Alright, so continuing to Chapter 6 of Christopher Tapp's Matrix Groups for Undergraduates. Just to remind you, that's what we're working through this lovely book right here. So in Chapter 6, Tapp gives a pretty nice presentation of the analysis needed to understand the convergence or divergence of series of matrices, which is nice. A little bit beside the point for our main exposition here, so I'll just assume it and just tell you what the result is, namely that this exponential of a matrix converges for any matrix A. And not just that it converges, its convergence is absolute, and which means we avoid the annoying things like Riemann's rearrangement, the rearrangement of conditionally convergent series. There's some really subtle stuff that goes on there. No such problem here. This is absolutely convergent, which basically means you can rearrange terms and differentiate and integrate, and it's all good. So in other words, even if you're not good at analysis, the structure here is very forgiving, and you'd have to work pretty hard to make a mistake. I'm sure we can manage, though. Anyway, let's get to it here. So a path. All right. Oops. A path from some open interval around 0 to Rm is an integral curve of a vector field f. And remember, we're taking the viewpoint that a vector field is a mapping from Rm to Rm, where we're basically saying, okay, so at point x, you're attaching f of x. All right, that viewpoint again. Anyway, that said, it's an integral curve. Alpha is an integral curve of f if the velocity field of alpha matches the f at alpha of t. All right, so this is the definition in our current context of integral curve. More generally, an integral curve of a vector field is just a curve whose tangent field lines up with the vector field. Okay, that's a simple, intuitive characterization of it. Now, I would encourage you to look at page 84 for more on the motivation and importance of integral curves, and page 85 for proof of the proposition below, which is also very pretty. So if A is in the general little glnk, right, which just means that A is an n by n matrix, the path gamma from R to the n by n matrices over K defined by gamma of T is exponential of TA is differentiable, and the derivative is just A times gamma or gamma times A. Since A commutes with every term in the series, it commutes with the whole series like so. And the proof, if you took my differential equations you've seen, it's essentially just using that absolute convergence and differentiating term by term, tilt your head, squint, and there it is. So another proposition which we shall use, I believe, is this. If A is an n by n matrix, you can look at that curve, the exponential, so-called, exponentiate the matrix with parameter t. And then for all x and kn, the curve alpha of t, r sub gamma, so multiplication by gamma of t of x. This is an integral curve of r of a, meaning that alpha prime of t is, where was I? R of gamma, gamma sub t of x. Well, not of x, of alpha of t. Likewise, alpha of t equals to L sub gamma t of x is an integral curve of L sub a. So you get integral curves naturally associated with this exponential, and moreover, if gamma of t is an integral curve of the vector field on MNK, whose value at g is a times g, let's see here. I'm trying to think of how to explain this. So number one is saying that if you feed the gamma, the exponential, into the right or left mappings, you get integral curves of the right or left maps. And number two is saying that gamma of t is itself an integral curve of the vector field whose value at g is a times g. So it's an integral curve of just the multiplication by a mapping. What is G? Oh, it's a matrix. Okay. I mean, the L sub A and the R sub A were mappings on Kn, whereas this is a mapping on the set of n by n matrices, so it is a different kind of thing. All right, anyway. Yowzers. Got some thunderstorm going on outside. That's scary. All right, so moving along here. Properties of the matrix exponential. If a and b commute, then e to the a plus b is e to the a times e to the b, which is not that hard to prove in the commutative case. Also, if you have an n by n matrix over k, then e to the a is an invertible matrix. So that means that the exponential is a mapping from little gl to big GL. All right. Likewise, if a is in little on, then e to the a is in big on. So the exponential goes from the Lie algebra, n by n orthogonal Lie algebra over k to the n by n orthogonal group over k. All right. And this is a story that plays out again and again in the theory of Lie groups. The exponential takes you from the Lie algebra to the Lie group. Maybe not the whole Lie group, but certainly some part of it close to the identity. All right. Proof of 1 is just brute force calculation. I'll leave that to you. For number 2, it's easy enough to prove with number 1 because a commutes with minus a. So e to the a plus minus a is equal to this. But a plus minus a is 0, e to the 0 is easy to see is the identity. So consequently, e to the minus a is the inverse of e to the a, which then shows you that the exponential is invertible for any a. And then to prove 3, you notice that if you have this either, well, it could be skew symmetric or skew Hermitian or skew I said skew symmetric or skew Hermitian or skew symplectic. Then again you can calculate e to the a times e to the star, or which is conjugate transpose, right? And in general, and so that's this. So this is a little lemma that the star of e to the a is e the exponential of a star. And anyway, so that's equal to minus a, right? Which is giving you back I. So you can see that e to the a is an onk because it satisfies the equation e to the a parentheses star equals to identity, which is the defining relation for the orthogonal group over k. And of course I leave this little, I left a little lemma to prove there that the exponential of a star is equal to the exponential of parentheses a star. Okay. I don't have anything to say about it at the moment. I mean, also this is continuing the properties. 4 is that the intersection of little sun and sun is given by the intersection of the Lie algebra of the unitary group and the Lie algebra of the special linear group. So this is a Lie algebra statement. And 5, which we will prove, is that the determinant of the exponential is the exponential of the trace, and that we're going to prove for R and C. I mean R or C. I don't want to be associated with the R and C. I'm sorry, excuse me. What was I saying? Alright, let's see here. So f of t is equal to the determinant of the exponential of t times a. That's the definition. Then if you calculate the derivative of this thing by the usual limit quotient, then you can use properties of the matrix exponential to rewrite that as e to the ta times e to the ha, and you can factor out this e to the ta because, oh by the way, because ta and ha clearly commute, so you have the usual exponential matrix exponential law. Sorry, I did something, I don't know. Anyway, it's been a while since I made that mistake, so let's see here. So then we have pulled that out. We're left with this terms with h, and then of course you can look at that and tilt your head and squint and say, ah, well that's the derivative at time 0 of the matrix exponential, right? So there you have it, e to the ta, this limit, but that limit is exactly the time 0 derivative of the determinant of the exponential. But we proved before that that's equal to the trace. Let's see here. Well, what do I got here? Determinant of e to the ta. So gamma prime of 0 is a. So the derivative of the determinant times 0 is equal to the trace. I believe I'm using the lemma from before that we already proved. That someone was somewhat involved to prove this, but we have proved this before. See here. Trying to see here, the trace. So gamma prime of 0 is a, so the trace of gamma prime of 0 is trace of a. It really is that lemma we used before. Let me not talk myself out of it. All right, so we have derived then the equation f prime of t is equal to f of t trace of a, which is good because we can recognize that as a differential equation, right? We have basically dy dt is equal to y times trace of a, and we know an initial condition, which is f of 0 is 1, and so that has solution e to the t times trace a. As you can easily check, it differentiates, satisfies the differential equation, satisfies the initial condition. So by the uniqueness, fundamental, uniqueness and existence theorem of ODEs, f of t is e to the t trace a. And then you just plug in t equals to 1, and out pops the identity we want, which is the exponential of the trace is equal to the determinant of the exponential. Now, I might ask this on like a linear final, but if I do it there, I guess I wouldn't be expecting this argument. That would be kind of draconian. I usually would give them this one little extra bit of information that the a was diagonal, right? When a is diagonal, you can show that the if v is an eigenvector of a, then v is an eigenvector of e to the a with and then so if v has eigenvector eigenvalue lambda with respect to a, then v has eigenvalue e to the lambda with respect to e to the a. So they share, eigenvectors, of course, with different eigenvalues. Anyway, long story short, of course, the determinant is the product of the eigenvalues, which just ends up being like, e to the lambda 1 times e to the lambda 2 times e to the lambda 3, e to the lambda n, however many you got. And then usual laws of exponents say, well, that's e to the lambda 1 plus lambda 2 plus plus lambda n. Of course, the sum of the eigenvalues is known to be the trace, and there you have it. So this identity is easier to verify in the case of diagonalizable matrices, but I'm not making any such assumption here, so we need a more general argument, and this is a standard argument for that. I think I'll leave the proof of claim 4 to the reader. It's probably not hard, but I'm gonna move along here. Actually, I'm just gonna stop right here for a second, and then I'll start up again.